Hi, everyone. I'm Josh Rackers, and I'm a Truman Fellow at Sandia National Labs here in Albuquerque, New Mexico. And I'm sorry that I can't be there with all of you today, but I am very excited to talk to you a little bit about what I think is a killer app for e3nn and Euclidean neural networks, which is predicting molecular electron densities. I'll start with a little bit of an introduction, since I'm sure I'm new to many people in the audience. I grew up in Ohio and went to Ohio State for undergrad. I got degrees in physics and political philosophy, and didn't actually know that I wanted to go into science right away. So I applied to an organization called Teach for America, and I was placed in inner city Baltimore, Maryland. So I became a high school physics and chemistry teacher for 3 years. I ultimately did decide that I wanted to go back into science, and so I got a PhD in biophysics from Washington University in St. Louis, and then started as a Truman Fellow 2 years ago here at Sandia. And just to zoom way out and tell you a little bit about why I think electron densities are an interesting thing, I think of what I do as part of what I call the grand challenge of molecular science. And the grand challenge of molecular science goes something like this. Say that I wanted to predict the behavior of some arbitrarily complicated molecule, like this is the coronavirus spike protein. Can I predict the behavior of that molecule from first principles? Now, of course, this is a really hard problem. Simulating big molecules is challenging. But at a conceptual level, we actually think this is very simple. In other words, we know the tools that we need to do this. We know F equals ma, which tells us how atoms move whenever you push on them. And we know how to get those forces, which is with the Schrodinger equation. But what I don't need to tell all of you probably is that this is the really tough part about the grand challenge. Solving Schrodinger's equation for something that is this big is next to impossible. So let me sort of quantify what I mean by impossible before I tell you how we're going to try to solve this. By impossible, I mean that this problem of solving Schrodinger's equation scales horribly. So I'm showing a little example here of computing the electron density for progressively bigger sets of water clusters from 1 up to 6. And this is the time it takes me to do this calculation on my laptop. You can see that, for 1 or even 6 water molecules, this isn't so bad. This is about an hour. But the scaling is really starting to take off here. And the estimate is that if I wanted to do this for 50 atoms, this would take something like 2 months. And for 100 atoms, this could take like 20 years. And which means that, if we want to do something like the spike protein, then we're just out of luck. So, you might push back on me and say, well, that's just your laptop and you're doing coupled cluster, which is like gold standard stuff. What if we do something more reasonable? You work at a national or a Department of Energy lab. Don't you have access to big supercomputers? So let's see what happens if I go down that road. So this little dot represents the computational power of my laptop. If that's true, then this giant circle extending off the screen is the power of the Summit supercomputer at Oak Ridge National Lab. So what if I try to do those same calculations as on the last slide, but on Summit? For 100 atoms, the estimate is, okay, that would take about 6 minutes. That's not so bad. We can wait 6 minutes for an important calculation. What about 100,000 atoms? This would take 42 ages of the universe, even on Summit. So the point here is not to belabor how hard quantum mechanics is, but just to say that this scaling problem makes large calculations impossible. Not just impossible like let's build a bigger supercomputer impossible, but physically impossible, at least on classical computers. So what we want to do, and myself and many other people, is to circumvent this problem by using machine learning. Right? We want to replace this expensive quantum calculation with a neural network or some other type of machine learning algorithm that can predict the forces that we can use to simulate things. And of course, the reason here is that neural networks, if constructed appropriately, scale linearly as opposed to polynomially like the examples I just showed you. Okay, so there's lots of different ways that you could envision doing this machine learning approach. Why do we want to learn the electron density? So the first reason I think we should learn the electron density is because of the issue of training data. Let's say that we want to simulate some arbitrarily large molecule like this. This is LOVD. This is an enzyme that's important in heart function. I just got done telling you we can't do quantum calculations on this whole thing, so we got to split this into pieces to build a training set, right? So these are all like the relevant chunks that you would envision having a part to play in the mechanics of this protein. But what you've done whenever you've constructed these training sets is you've imposed a sort of effective radius on it. In other words, if I'm just picking this number out of a hat, but if the largest distance between any two atoms in this training set is 10 angstroms, then that means that the model itself cannot see anything outside of 10 angstroms. But why is that a problem? I picked this particular protein because it's interesting from an experimental standpoint. All of these here, denoted in red, are all mutations, and all of these mutations directly affect the structure of this enzymatic pocket. They're important mutations to the function of this enzyme. What's interesting is that all of these mutations are more than 10 angstroms away. Some of them are more than 15 angstroms away. And what that means is that it's going to be exceedingly difficult to capture long-range forces like this if we can't include them in the training set. So the solution to this, I think, is that rather than learn energies or forces, not that I'm saying that those are bad things to do, I think Simon and Albie just gave a very strong argument for how effective that can be for short-range interactions. But for long-range interactions, I think the solution is instead, let's learn the electron density. So now instead of having local forces on any of these, we have local densities, and we still have this training data. We still have the limited size of training data. And so these are still local densities. But these densities now, they can interact with each other, right? We know the laws of physics that tell us how electron densities push on each other. You know, this requires no machine learning. And so that's the reason, the fundamental reason that we want to learn electron densities is because they can give us access to long-range forces that would be impossible to get otherwise. Okay, and so this is the part that I'll go fast over because you've been sitting in a tutorial on equivariant neural networks all day. But of course, the electron density is not just any old object. It's a unique object. It's a three-dimensional function, a scalar valued function in three-dimensional space. And so we really, really, really want, in fact, need this property of equivariance that's been talked about today. Just to show you a simple example, if there's a p-type function representing a density contribution on this atom, if we rotate this structure, we want that density contribution to rotate with it. So, you know, the big picture here is pretty simple. Instead of using just any neural network, we want to use a Euclidean neural network to do this prediction, and we're going to predict electron density rather than atomic forces. And then we'll rely on physics to get forces once we have that density. And so for this tutorial, I'm really going to focus just on this part. I'm not going to talk at all about this. And that's not because this isn't important, but because, you know, it's not the focus of today, and there's a lot of interesting details that make this step kind of hard. So if you're interested in this step, talk to me offline. I'd be happy to talk about it. But let's jump into our collab. Okay. Let's page up here to the top, to the beginning. So there's basically 7 things that I want to cover in this collab. And what the big picture here is that we're going to teach you how to use e3nn to predict an electron density. And we're going to do that in a sort of specific way. So we're going to first explore what an electron density is and how to represent it mathematically. We're going to explain the inputs and outputs for the neural network that will be predicting that density. We're going to construct a data set. We're going to use some of the models that are already in e3nn so that we don't have to build our own. We're going to train a network. We're going to analyze the accuracy of that network. And then we're going to see how well it can do this extrapolation trick. In other words, if we train it on small things, how well does it do on big things? So let's start with doing some imports here. We need a couple of different things, none of which are terribly important in details, but just to mention them while this is going. We need the various components of PyTorch geometric, which is essential for e3nn. We need e3nn, of course. We're going to need WANDB, which is a nice little utility for watching training whenever you're training any type of neural network. We're going to use Plotly for plots. We're going to use this Gao to grid utility to do some data handling. And then we need this utils.py, which is just a grab bag of utility functions that I'm hiding from you to do some of the messy stuff. Okay, so that's great. We've downloaded everything. Now let's talk about the electron density. So again, the electron density is a scalar value over all three-dimensional space, and you could envision that, probably envision that there's lots of different ways you could represent an electron density. For instance, a fairly simple but not very good way would be to just put it on a grid. So every grid value gets an electron density. A much better and more data efficient and more accurate way to represent a density is using what's called a basis set. And basis sets are sums of functions that have this form: some spherical harmonic times a radial function. And in quantum chemistry, the radial function that we choose to use is almost always a Gaussian. So this is this alpha parameter, which controls the width of the Gaussian, and then this r squared, which tells us that it dies away as we go further and further away from the atom. Okay, so let's look at the spherical harmonic part first. So first, we're just going to create a grid here from -2 to 2, and we're going to find r, theta, and phi for every point on that grid. And we're going to need r, theta, and phi for what we're going to do next, which is to plot the spherical harmonics. So this real y is the real spherical harmonics. It's a utility function that we imported from this utils.py file. And so let's plot what one of these spherical harmonics looks like. For instance, this is the spherical harmonic with L equals 1, M equals 0. All right, and this has a very familiar looking plot, right? This is a vector-like spherical harmonic, so this is pointing in the z direction here, because this is m equals 0, and it has the positive lobe and the negative lobe. But we can also do this for arbitrarily high L. So this is the same thing, but for L equals 5 and M equals 3. And you can see that this is a lot more complicated, but still, the same basic idea of a spherical harmonic. And what you can probably appreciate is that these spherical harmonics, as you go up in L, give you the ability to get finer and finer grain resolution on the angular part of whatever function that you're trying to represent. And I don't think that we'll be using L equals 5 for any of the densities here. I think we just go up to L equals 4, but you can, of course, get the point that the finer grain detail that you need, the more spherical harmonics and higher L spherical harmonics you can add. But of course, one really important thing to notice here is that there's no radial decay that's happening. The spherical harmonic is just going to keep going in every direction. And that's because we haven't added in the radial component, right? We've just been plotting this. So what does this part look like? Well, that's much simpler. This is just a Gaussian. And the width of the Gaussian is controlled by this parameter here. So if I make this bigger, then the Gaussian gets more narrow. I can make it a lot bigger, and now we get a very narrow Gaussian. Or I can make it smaller and get a much more diffuse Gaussian. And so we can pick this alpha parameter to be whatever we want, whatever is useful for representing the density. So let's put them together. So here's our spherical harmonic part, here's our radial part, and we're going to plot a basis function, which is the most important type of basis function, which is the one with the spherical harmonic where L equals 0. And these are going to be the ones that are spherically symmetric. And believe it or not, these types of basis functions end up representing the bulk of the electron density of any given atom. And you can see that this has the expected behavior, right? It's very dense near the atomic center, and it decays as you go further out. But of course, we need more than just L equals 0. We're going to need some higher L1. So this is an L equals 2 example here. And you can see that these ones with higher L have positive and negative lobes. And so these will add to the density in a given region, and these will subtract from the density in a given region. So of course, our electron density isn't going to be represented by any one of these basis functions. It's going to be represented by a sum of them. So that's what's represented here in this equation. And the sum, each of the elements of that sum is going to have a coefficient. So let's look at how that is here. I've arbitrarily defined, you could pick whatever you want, 9 basis functions, and L equals 0, L equals 1, L equals 2, and a set of coefficients that go with each of those basis functions. And I'm going to define the density to just be the sum of all of those bases times their coefficients. And you can play around with this as much as you'd like and change these coefficients and see how that changes the density. One thing to point out as this is plotting is that I've picked the coefficient of the L equals 0 function to be much bigger so that it represents the spherical component of the density. And so you can sort of see that this is a kind of a funky looking density that you could conceivably have around an atom. And these coefficients here are picked out of a hat, but in a real calculation, these coefficients are the output of your calculation, right? So these define the density. So let's look at that. Let's look at some real data. Let's talk about what the inputs and the outputs of an e3nn electron density model are going to be. So let's go ahead and download a data set from my Google Drive. And this data set is called the W10 data set. So these are all, I think 1,000. Let's check here. Yep, 1,000 structures, different structures of 10 water molecules in varying different arrangements. And let's just take a look at what's going on here. So these are the coordinates for the first structure. This is the first part of the input, which is just the coordinates. These are the X, Y, and Z coordinates for all 30 atoms in this 10 water molecule structure. And correspondingly, we have element types. So this 8 is the atomic number for oxygen, 1 for hydrogen. So we have oxygen, hydrogen, hydrogen, oxygen, hydrogen, hydrogen, so on and so forth. And believe it or not, that's all the network needs. It just needs to know where is the atom and what type of atom is it. The outputs are a little bit more complicated. So remember that the output is the electron density, and we're representing the electron density as the sum of basis functions. And each basis function here has 4 components that are necessary to define it. The first 3 are all predefined by what's called a basis set. And that is the L for a given function, the M for a given function, and the alpha for a given function. The fourth one is the actual thing that we want to learn, and that's the coefficient that corresponds to that basis function. So let's take a look at what that kind of looks like for an example. This is the first atom, so an oxygen atom, in the first structure. And we have this table, and I think that there's, if I remember right, 70 different entries in this table. And each entry in this table is a different basis function. There's L, there's alpha, and there's the coefficient. I'll talk about M in a second. So like I just said before, these L's and these alphas are all prescribed by this basis set that we've picked to represent the density. What's changing are the coefficients. So a change in density is represented by a change in coefficients. And again, each line is a different basis function. One thing you'll notice is that the M's are missing here, and that's just because of the M's are implied. So e3nn has a particular way that it orders the m's for each spherical harmonic, and we follow the e3nn convention for the ordering here. All right, so let's just verify from this table that what I have in my data set is actually the same thing. So the first coefficient is 1494, and that is the same. And the alpha is 2,876, and that's the same. Ooh. Okay, good. So that's our raw data, and hopefully this makes sense. So again, we have x, y, z, and atom types that are the input, and then coefficients that are the output. All right, so excuse my corny graphic here, but now we need to turn this raw data into data that e3nn can use. And we're not going to delve into all the messy details here. I've hidden most of it away in this get iso permuted dataset function that's in this utils.py. The first thing that we're going to need to use with this utility is the densities of isolated oxygen and hydrogen atoms. So rather than learn the full density, what we're going to do is we're going to subtract away the density of isolated atoms from each atom, if that makes sense. So what we end up learning is sort of a delta, a difference between the isolated non-interacting density and the full density. So here we're calling this get iso permuted data set. We're feeding it this data set that we've downloaded, and we're also feeding it these isolated oxygen and hydrogen. But what we can see is that even after doing this, it's still got the same information, right? So it's still, we still have our positions here. We still have our input atom types. I'll note that we're changing now. It was 8 and 1 before, and now we've switched to a 1 hot encoding, which we find works better for the network. So this is 0, 1 if it's hydrogen, 1, 0 if it's, or excuse me, 0, 1 if it's oxygen, 1, 0 if it's hydrogen. And of course we have the coefficients, and notice now that this first coefficient is not the same anymore because we've subtracted away the isolated oxygen, in this case density, from the atom. Okay, but yeah, as I note here, the most important thing is that now this data set is in a form that e3nn can use. In other words, it's a torch geometric object, data object, and so we can use it to make a molecular graph, and that's exactly what e3nn is going to do. Okay, so let's go ahead and make an e3nn model. So what we're going to do here is construct a model from one of the models that exists already in the e3nn repository. And I'm not sure that this is well known, so I'm just going to point out where this lives. If we go to the e3nn repository and we go into the source code and we go to neural networks, there's this folder here called models. And I've played around with several of these, and they all give really excellent results, and they all work. And so you should feel free to use one of these rather than try to have to construct your own on the fly. So I'm using this gate points 2101. Okay, and let me just walk through the arguments here because it's important to understand what's going on. So first, erep's in. This is telling us, okay, what is the erep? What is the representation for the input data? And of course, this is that 1 hot up here. So these are 2 scalars. And this is exactly, I'm going to assume that everyone saw this before, that this is what's being specified here, 2 scalars. Now we're going to specify the ereps for the hidden layers. And this is going to tell us essentially how big that the network is. So in this case, I'm saying I want 10 scalars, 3 vectors, 2 rank 2, and 1 rank 3. And this negative 1, 1 is just telling me that I want the even and odd versions of each. So this is a hyperparameter. You could change this, and this would be a key place to try to make the network more accurate. This is super important. So this is really at the core of why e3nn is uniquely suited for this task. So if you remember, our outputs are these coefficients, but each of these coefficients is associated with a given L, right? For instance, there are 12 L equals 0 coefficients, and I can't remember how many L equals 1 or L equals 2, but you get the point. The network needs to know when it's predicting a given coefficient, what does this belong to? And so that's what's being done here in eReps out. Sorry for the paging. This is saying there are 12 scalars, 5 vectors, 4 rank 2, 2 rank 3, and 1 rank 4 things coefficients to predict from the network. If we were to mess this up, we would lose equivariance, right? We would lose this property. So this is really at the core of what makes e3nn the right tool for this job. It is capable of outputting things that have this geometric quality that we want. These are both hyperparameters that can be played around with. This is also a hyperparameter. It tells us the number of hidden layers. This tells us the radius for the convolution, and it's tied to this number of neighbors. So the number of neighbors in a given convolution is usually around 12. These are hyperparameters for the radial function, and these you can pretty much safely ignore. So let's go ahead and load that up. And again, feel free to use these models that are already built in the repository at will. And let's just do this boilerplate PyTorch stuff to move the model to the GPU. I find that a high learning rate works just fine for this task. Okay, and now let's train the model. So I'm not going to go through everything here. I'm happy to answer questions if people want me to walk through this in detail. But this is, training the model, and we're going to collect some error metrics on this as we go. And I'll note that this is sort of a toy problem. We're just going to train on 10 examples, and we're going to test on 10 examples. And we're going to use this nice utility WANDB to track training. So if we click this link here, this opens this up, and as soon as we finish our first epoch, there will be data here to look at. So let's go back and see here. And while this is going, I'll just sort of explain a little bit what we're looking at here. So now there should be data here. Yep. So we're going to look at a couple different things. The most obvious are the loss functions. So this is the training loss, and this is the test loss. You can, yep. And the second thing to look at are what's called EPS, which is a measure of density similarity. An EPS of 40 is really bad. This means densities are not very similar to each other at all, but an EPS of about 1 would be state-of-the-art for density similarity. And you can see that just in this first epoch, of course, the train loss has gone down, and this WANDB utility gives us a really nice tool for tracking training in real time to make sure that our model is doing what we think that it is, that it should be doing. And so we see nice behavior here, right? The training loss is going down, the test loss is going down, and these metrics, the EPS for the test and the train set, are both going down as well. Sometimes there's a bit of a lag, so it doesn't hurt to refresh the page. Great, so you get the idea here. So let's go ahead and stop that. We're not going to wait for the full training here. And we're going to go ahead and load a pre-trained model that I did earlier today. So we've downloaded this from my Google Drive and loaded those weights into the model. And let's go ahead and look at some densities. So we're going to generate the density on a grid for the first structure in the test set. So this is executing the model here. So this is kind of buried here, but here's the model. And then we're going to generate a grid, and then we're going to use that model, here's the argument, to get the density on a grid. So this might take a second. Oh, there we go. And then let's plot this and see how the target density looks compared to the machine learned density. And this is using a utility called Plotly, which is a really nice little library. It does take some time to render 3D plots, but they're interactive, and that's kind of fun. So here's the machine learned density on the left, the target density on the right, and what you can see is that these are virtually indistinguishable. If you try to zoom in here, you're not going to really see differences between this machine learned and target density. So let's look at something a little bit more instructive, which is the difference between these two. So now we're taking the machine learned minus the target density. And we're going to plot that. And what you can see is that this density is very accurate. So this is, notice the scale here is tiny. This is 0.04 to negative 0.04 electrons. And the error is all localized to these tiny areas around the nuclei. And so, if you compare this and the scale of the error here to the overall density here, you can see that this model does quite well at this density prediction task. All right, last thing. I promised to talk about extrapolation. So let's see how well does this model do whenever we try to use it to make predictions on larger structures. So let's download a 53 water structure, which is just about the biggest thing that I could do a reference calculation on. And we're going to change it into a torch geometric data set so we can use it here. And let's execute our model now on this 53 water structure. So we're doing the same thing here, but now with something that was not in the training set and much bigger than anything 5 times bigger than anything in the training set. So now we have the density, and let's plot it. This might take a second because it's a much bigger structure. But we're essentially doing the same thing as above. We're gonna plot the density on a grid, and we're gonna look at the machine learned density versus the target density. And here you go. And just as before, if we look at these things and we zoom in, it's very difficult to try to parse out where the difference between these machine learned and target densities is. So let's plot the difference again and see how that looks. And here we go. And just like before, the scale is very small, and we might say that the magnitude of these errors may have gone up a little bit, which is possible. But the point is that compared to the overall magnitude of the density, these errors are very localized to the nuclei and very small, still within this 0.04 to negative 0.04 electrons range, which is really, I think, quite remarkable. And I'd just like to take a second to point out that this is looks very easy in a Colab notebook, but very important that we were able to train on something that's a small scale system of 10 water molecules, and that it does almost equally well on this much larger system of 50. So with that, I'd like to just briefly kind of wrap up with some slides that show you a little bit more science on what you can do with this at a sort of production scale. So a grad student, Lucas Tico, who's at UCLA, has been working with me, and he came up with a nice experiment to test this extrapolation phenomenon. So he put together all these training sets of increasingly bigger clusters of water molecules from 7 all the way up to 25. And he trained models on each of these, and then he tested all of those models on this 30 water molecule test set. And what he found was really interesting. For the small training sets, so 7 or 8 water molecules, you see the expected behavior on the test set, which is that the error goes down. The bigger things look more like the bigger test set, so you get a better performance. But what he found is that around 12 water molecules, this starts to plateau. In other words, around a radius of about 7 angstroms, you don't need information from any further away to get a good prediction of the electron density. Including these bigger structures really doesn't get you much. And that's saying something really important, because remember that the whole promise of this scheme was that we would use it to get long-range forces from short-range training data. And this is sort of indicating that that's probably true. Another interesting thing just to point out is that e3nn does its job in a very data efficient way because it has these higher order features in the network. So I'm doing an experiment here called a learning curve, where I plot the number of training samples on the x and the error on the y. And each of these is a different model with the hidden layers configured differently. So this curve is with the hidden layers with just scalars in it. This is with scalars and vectors. This is with scalars, vectors, rank 2. You get the idea. And what's really interesting here is that all of these models learn. In other words, as you add more training data, the error goes down. But the bigger L max is, the faster you learn. Just to kind of pick out a data point here, a model with L max of 2 achieves the same accuracy with 100 samples that you would need 10,000 samples for with an L max of 0. So this gap here, this is equivariance at work, right? This is saying that having these higher order features really improves the ability of the model to learn. And what's neat, and I'll kind of leave you with this, is that you don't have to just use this for water. I'm not showing it in the Colab notebook, but we've been able to do similar calculations for DNA. So this is a machine learning prediction of the electron density of an experimental crystal structure of DNA. And you can see that the difference between the machine learned and the target is quite small, even for this very large structure. And one really interesting thing you can do with this for DNA is you can use the density to calculate an electrostatic potential. So this is the electrostatic potential of this base pair here. And what's kind of cool is that this machine learned electrostatic potential outperforms the leading method for computing electrostatic potential with a classical force field. That's really neat, because you could use that potentially for predicting binding sites of proteins or whatever you'd like. And what's really cool is because of the scaling properties of our neural networks, you can do calculations that are completely outside of the realm of possibility for quantum mechanics. So here are some predictions on the canonical B-form DNA, the so-called Drew-Dickerson dodecamer, a stacked Holliday junction, which is really interesting to people that want to do kind of structural design with DNA. And here's something crazy big, a nucleosome core particle. This is how DNA packs in our cells. And this is a prediction on close to 10,000 atoms. This is something that would be entirely impossible, even with the biggest supercomputers, to make this prediction with a quantum calculation. And so with that, I'd like to thank all the people that helped develop the code and the data that I showed you today. And I'd like to thank all of you for coming by this tutorial. And if you have any questions about how to use e3nn, or questions about how to use it to predict electron densities, please don't be afraid to ask. Thanks.